Hello everyone and welcome to today's session. Today we will be looking at topic 1.8, which is called sum of infinite geometric series. Okay, so first, in order to begin the topic, I need some background, as always. Okay, the background will consist of two things. The first, just a quick reminder of geometric sequences and series a long time ago. So I'm gonna go over a little reminder. And the second thing is we will do experiment. So let's start. So what is a geometric sequence and a geometric series? Let's remember. If you So for example, a geometric sequence is something like this. It's a list of numbers, 4, 8, that are obtained in a very specific way. It's not just any list at random. Okay, the particularity of this list is that every new number in the list is obtained by means of the previous one. How? By a multiplication by a constant number. In this case, how do I get 2 out of 1? Well, by multiplying by 2. 1 times 2 is 2. And in the same way, the 4 is obtained by multiplying 2 times 2 is 4. And 4 times 2 is 8. This is what we know as a geometric sequence, when each new number is obtained by multiplying the previous one by a constant number. Let me give you another example. Let's begin with 3, and then 12, and then 48, and then etc. So by what number did I multiply 3 to get 12? 4. This is going to be kept throughout the sequence. 12 times 4 is 48, and so on. So these two are examples of sequences. I'm going to label this as sequence 1. I'm going to label this as sequence 2. Also, remember that for sequences, we found some terminology and some formulas. For example, for the first sequence, the first term, A1, is 1, and the ratio, do you remember that word? Is 2. Remember that the ratio, R, is the number by which we multiply to get all the following numbers. Also remember that when we write A sub n, what we mean is the nth term of this sequence. And there was a formula for that, which was this. Okay? If you don't remember this, that's perfectly fine. I've been telling you all this semester that memorization of formulas is not a mathematical ability, okay? What to do with them once you look them up is what I'm expecting out of you. Okay, so that's a geometric sequence, okay? Now, what was a geometric series? Remember, this word series is just another word for sum. In the first case, when I have this sequence 1, 2, 4, 8, I can sum, for example, the first two terms. And this is read as the sum of the first two terms of this sequence. And that would be 1 plus 2 equals 3. I can sum the first three terms of the first sequence, and that would be 1 plus 2 plus 4, which is equal to 7. I can add the first 10 terms, okay? and so on and so on. So that was what geometric series was. Okay, it's just the sum of some of the numbers in a specific sequence. Okay, that's all it means. And remember that we also found the formula to get the sum of the first n numbers of a geometric sequence, and that was equal to the first term times the ratio elevated to the n minus 1 over the ratio minus 1. This is the formula that gives us the sum of the first n terms of a geometric sequence. Again, if you don't remember this formula, that's perfectly fine. I confess, honestly, I never memorize these things. I always look them up. I can find them and I can get the formulas on my own if I want to, but I never memorize them. That's a completely stupid method, okay? It doesn't make any difference because you have books to look them up and you have Google. It's a good idea, but it's not the best idea. Okay, let's move on. So that was a reminder about geometric sequences and geometric series. Now let's go on to the experiment that I told you. For this experiment, I need you to grab your calculator, a pencil, and a piece of paper. It doesn't have to be your notebook. I give you 25 seconds. Go ahead. Okay, that's enough. I don't know if that was 25 seconds, but let's move on. Okay, the experiment is the following. Let's suppose that we have a number a such that a is in between minus 1 and 1. Or in other words, a is greater than minus 1 and a is less than 1. Or in a pictorial way, a lives in this zone. Okay? Only in this zone. For example, it could be 0.5 or minus 0.8 or minus 0.1, something like that. But it's strictly in this zone between minus 1 and 1. So let's suppose that. Now, the question that I want to ask you is this. What's going to happen if a lives in this zone and we raise a to a large exponent? Okay? What would happen if we do that? What would be this result? Okay, let's do that experiment. So let's choose one a that lives in here. Let's go with 0.5. Let's choose a equals 0.5 and get ready with your calculator. What I want you to do is the following. Let's raise 0.5 to the 1. That's very easy. We obviously get 0.5. Next, let's raise 0.5 to the 2. Let's do it. I'm gonna do it with you. You should get 0.25, right? Let's continue. 0.5 to the cube. Let's raise it. You will get 0.125. Now let's jump to raising 0.5 to the 5th. Let's do it. you're gonna get 0.03125. Now let's make a bigger jump. Let's raise 0.5 to the 10. Let's do it. What you get is 9.76. I'm gonna cut the number right here, times 10 to the minus 4. And remember, this is scientific notation. What that means is 0.0000976. So it's a very small number. Now let's make a bigger jump and let's raise 0.5 to the 20. Let's see what happens. What you get is 9.53. I'm going to cut the number right there, times 10 to the minus 7, which is equal to 0.000000953. So 0.5 to the 20 is even a smaller number than before. So pay attention to what we're doing. What are we doing? We are raising 0.5, which is a number between minus 1 and 1, to increasingly bigger exponents. And what can you see? What is the pattern? What happens when we increase the exponent more and more and more and more? These numbers, the results, get smaller and smaller and closer to 0. When you get to such a large exponent, say 1 million, you're not going to be able to do that in the calculator, okay? I don't think it's going to happen anything. Let's do it. You're going to get a 0, right? Did you do it? The calculator said 0, but the calculator is wrong, okay? It's not 0. It's something extremely close, but not 0. The reason the calculator gave you 0 is because technical stuff that I'm not going to go into, okay? But it's not 0. It's a number so tiny that it's almost 0, but not 0. I want you to be extremely aware of that. This number is not 0. It's just very small. Okay, so what is the conclusion of this? When we raise a number between minus 1 and 1 to a very large exponent, we get something that is extremely close to 0. Extremely close to 0. And the same happens whether it's 0.5 or whether it's minus 0.8 or minus 0.1. Any number in here will happen to behave in the same way that the 0.5 behaved. Okay? Let's move on. I want you to realize also that the same doesn't happen when the number that you try is not in this zone. For example, if you choose the number 2 for that experiment, you will have 2 to the 1 equals 2, 2 to the 2 equals 4, 2 to the 5 equals 32, 2 to the 10, 2 to the whatever, let's say 100, you're going to get bigger and bigger results. So when you raise something outside this zone to larger exponents, the answer, and by that I mean these numbers, the answer just keeps growing, okay? It doesn't get close to anything, just like the case before, in which these numbers were getting closer and closer to 0. Okay, so I'm gonna write a more precise statement about what we found. What we found is this: if a, which is a number, is between minus 1 and 1, a to a large exponent, and this is a very technical phrase or a very mathematical phrase. but that's okay. Then a raised to a large exponent converges in mathematics. This word converges to zero. And this is just a fancy word to say the following: approaches zero. This phrase and this phrase mean the same. Or let me give you another one. Get zero. All these three phrases, mean exactly the same. So this is just a mathematical word, a fancy mathematical word. Okay, now we have all the ingredients to go into the discovery of today. Remember, the name of the topic was the sum of an infinite, that is a key word here, an infinite geometric series. Let's see what that means, the part of the infinite. I'm gonna do this. I'm going to write two geometric sequences. This one that I already touched upon, 1, 2, 4, 8, and this other, 1, 1 half, 1 fourth, 1 eighth. For these two sequences, we have that their first terms are 1 for both of them, and the ratios in the first case is 2, and in the second case the ratio is 1 half, or 0.5. Okay, now we also talked about their series, right? The series, or the sum of the first two terms for this particular sequence, is 1 plus 2, which is 3, and the series, or the sum of the first three terms of this sequence, is 1 plus 2 plus 4, which is 7. Now for this one, S2 is equal to 1 plus 1 half, which is equal to 3 halves, or 1.5. And the sum of the first three terms is 1 plus 1 half plus 1 fourth, which is equal to 1.75. Okay, now here comes the important question. What if somebody asked you not to sum the first two terms of this sequence, not to sum the first three terms or the four terms, but what if he asked you to sum all of them up until infinity? All of them. Completely all of them. So what if he asked you this, the sum of an infinite number of terms for this particular sequence? What do you think would be the answer? The answer for this question is that this sum for this particular sequence, okay? The sum would be an infinite number, right? Because it makes sense. If the sum of the first two terms is 3, and the sum of the first three terms is 7, and the sum of the first four terms would be 15, and so on, we can see that as we add more and more and more and more numbers along this list, the sum grows infinitely, okay? So the sum of this infinite number of terms is simply an infinite sum, okay? That's all we can say. And so basically this problem doesn't have a clean, concrete solution, okay? Every time we talk about infinity, it's not very clear what we mean, okay? Maybe you will understand later what infinity is, but it's not really a number, okay? So for this particular problem, the sum of this infinite number of terms, basically what we say is that we cannot perform this infinite sum, because we don't get a straight answer. We don't get something like 3 or 7 or 1.5. No, we get something like infinity, which is not a very clear idea, okay? So we cannot perform this infinite sum. Okay, that's a bummer. Now, what if somebody asked me the same question, but instead with this other sequence? Okay, a sequence in which the ratio is 1/2 or 0.5, and which fulfills this, right? Being r equal to 1.5, I'm sorry, to 0.5, then r is between -1 and 1. So it satisfies the condition that we talked about in the experiment. Okay, let's see what happens. So could this sum, the sum of the infinite number of terms of this sequence, that is all of these terms up until infinity, all of them, could this have a straight normal answer just like these numbers? Yes, amazingly, that is possible. Okay, and I'm gonna show you how we can get to this idea or to this discovery. Let's first write the sum of the first n terms of a geometric sequence, the formula. So it's this. One more time. I already wrote it down, but I'm gonna do it again. This is the sum of the first n terms of a geometric sequence. It's equal to all of this. And basically, since I'm adding not just 2 or 3 or 4, but all of them, an infinite number of terms, what I need to do is replace this n with infinity. The sum of an infinite number of terms is equal to a1, the first term, times the ratio raised to the infinity minus 1 over r minus 1. Okay, we're very close to the discovery, okay? Just hang on. Now, I only want you to pay attention to this little term in here, this one. The ratio r raised to the infinity. What does that even mean? Okay, for the purposes of the course, I want you to understand this term in the following way. You're raising a number, r, to a very large exponent. Okay, I want you to interpret infinity as an extremely large number. Extremely large. We're talking trillions of, and even more than that. Okay, so what's going to happen to all of this? Remember, the ratio is between -1 and 1. So we are raising a number between -1 and 1 to a very large exponent. So tell me, how much is all of this enclosed in this blue line? How much is all of this? We already talked about this in the experiment. If you said 0 or close to 0, you were correct. This is something so extremely small, so close to 0, that for the purposes of this formula, we can simply ignore it. We can say that it is 0. Okay? So basically, what we can do is this. Let's write again. The sum of the infinite number of terms is equal to a1 times 0 minus 1 over r minus 1. Let's continue here. a1, the parentheses will be minus 1 over r minus 1. And finally, we get the following formula. And there you have it. Look at this. We get a concrete answer. The sum of the infinite number of terms of a sequence with this particular characteristic, that the ratio of such sequence is between -1 and 1, does have a concrete normal decent number, which is minus the first term over the ratio -1. This is the formula to find it. And that's it. Okay? I know it's hard to believe that a sum of an infinite number of terms could actually be something concrete, but it's mathematically possible. Now, let me tell you something. Let me tell you also this. This formula is also written commonly in this way: a 1 over 1 minus r. And I'm going to let this for you as a proof, to prove why this and this are the same. It's a very easy proof. Okay, so let's use this formula. The sum of the infinite number of terms is equal to a 1 over 1 minus r. Let's use it in one simple example, which is the same that we talked about before. This sequence has a first term equal to 1 and the ratio equal to 1/2 or 0.5, which fulfills the requisite of being between -1 and 1. So it checks. It checks. Then we can add all of these terms up until infinity by using the formula that we just discovered. We just have to substitute a 1 and r in this formula. So let's do it. A1 is 1 and r is 1/2. So what is all of this? 1 over 1 minus 1/2 is equal to 1 over 1/2. And if you do this division, 1 over 1/2, you're going to get 2. So the sum of all of these terms, which is an infinite number of terms, will be equal to 2. That's a concrete, decent number. Okay? And that's how we use this formula.